basics behind microscopy, of course, I'm not sure if most of you would have touched upon it in the basics, but if you understand how the images are formed and how it is, uh, the fundamentals lie in some of the courses which most of the electrical engineers do, which is digital signal processing. Okay. So, what I'll try to do today is I'll give you an overview of what transmission electron microscopy is and what are the ways in which you can look at the images and how do you understand the data that you get from it. And I'll give you some examples from MEMS based devices and some real time characterization. I hope I'll be able to complete this in, let us say, the next 1 hour or 1 hour, 10 minutes or so. And I'll get started. So, transmission electron microscope, as you can see here, is this sort of an instrument. But the main differences are the source that you use here is different. You use electrons, and the entire column of the microscope is maintained under ultra high vacuum. So if you look at it, the outline of today's presentation, I'll just give you some principles of microscopy. I'll try to show you what the transmission electron microscope is. In fact, I wanted to show a live demonstration, but because of some issue at the uh, instrument, that is, we didn't have the camera readily available there, I couldn't show the live demonstration. But hopefully, once some of you guys are here, we can do a practical hands-on session, and I'll give you a few examples. So, very quickly, can somebody tell me what exactly is a microscope?
To observe the microparticles, cells.
Any device that you can use to see features which are not visible to the naked eye, you can call it as a microscope. Okay. So, for example, if you see this, this is the simplest microscope you can think of, a magnifying lens. Yeah. Any idea who invented the very first microscope?
Robert Hooke.
Well, there are different conflicting theories. In fact, the first one who conceptualized the microscope was none other than Galileo Galilei. But the first one who patented the idea was Antoine von Leeuwenhoek. And around the same time, Robert Hooke was trying to understand the physics of things. So it is all the three together, I would say. So if you look at the microscope of van Leeuwenhoek, it looked like this. There's a small lens here, and you can see here there's a little stage with which you can move a sample sitting on top, up and down, or left and right. Can somebody mute that, please? I think it is Vipra Tripathi. I hear some background noise, so yeah, thank you. Yeah, so the idea is if you have a lens and if I bring a sample close or far away from the lens, I can zoom into it and then you can start seeing the features inside or on the surface of the lens. Now, how small objects can you see? Can anybody tell me, have you come across any criteria which define what a resolution is or how small objects can you see? Hello? Anyone basic?
How clearly we can distinguish two different points.
Yeah, that is resolution. And what exactly is resolution? Numerical aperture, yes, that is right. Any equation that can define all these things together? Is the resolution proportional to the wavelength or inversely proportional to the wavelength? K lambda over Na, yes, Rayleigh criterion, fantastic. So, like somebody was just mentioning, resolution is the ability to distinguishly see two closely packed features and to resolve them. And the resolution limit is defined by Rayleigh's criteria. If you look at the denominator, this is the numerical aperture, and the numerator is the wavelength. Okay. So, for any optical microscopy devices or any devices that use optical wavelengths, what is the resolution tentatively from this? What is the wavelength of optical radiation? The range? Hello? 400 to 700 what? Nanometers, yeah. So suppose if I use any radiation which has a wavelength of 400 to 700 nanometers, if I plug in all the numbers here, I'll approximately, in an ideal scenario, get a resolution of something in between 400 to 700, which is, let us say, 5 or 600 nanometers. That is in an ideal case. But in reality, do you think I'll actually get that number? No. Reason is, well, if you still achieve the diffraction limit, you would have gotten an extremely good resolution anyhow. It's not really diffraction, but the answer is there is something called as lens aberrations. Yeah. So the point is, if you look at the resolution of an optical microscope in an ideal scenario, you should be getting around 500 nanometers, but you are getting somewhere around 1 micron. But the thing is, with the development of nanotechnology and miniaturization of devices and so on, you want to achieve smaller and smaller resolving powers, which means you require smaller and smaller wavelengths. You can use corrections, that is right. We'll come to that, Atul. So the bottom line is the thought process of developing the so-called electron microscopes is if you want to achieve better and smaller wavelengths, you start using a different kind of radiation. And if you look at the entire electromagnetic spectrum, you can think of using X-rays, you can think of using neutrons, you can think of using gamma radiation, but there is a reason why we use electrons. The reason why we tend to use electrons is because these are charged particles and you can generate them quite easily either by thermionic emission or field emission, and you can control the path of an electron beam in a much better way than any of the other electromagnetic radiation. So, with that background, I can tell you this is how an optical microscope looks like. This is an image from a metrological device inside a clean room only. If you see, this is an upright compound microscope. It is run in transmission mode. The source here is in the bottom. You put a sample on a glass slide and the light goes through, and you have an objective lens here through which you reconstruct and you capture the image on a camera here. Now, if I have a technique which can see through samples like this, can anyone tell me what is the image that you see here on the right?
A rib
X-ray.
cage.
Sorry?
Rib-
It's an
X-ray of
X-ray
rib cage.
radiograph. And you start seeing features inside. So the reason why I took this example is you see a transmitted attenuated image as a result of X-rays. And as you can see, the bones which have a different density from the flesh and the muscles here appear with a different contrast. So if I think of a technique in which I use a microscope, which also uses radiation which can be transmitted through a sample, and then I start constructing a device, that is what is called as a transmission electron microscope. So to tell you how that looks like, if I turn the microscope upside down, if you see this number 1 that is written here is the source, the number 2 is a stage here, 3 is lenses, and 4 is where your detector is. The exact analogy, if I have an electron column which is mounted like this, with number 1 being an electron source, 2 is where I have my objective lens as well as the sample area. This 3 is a series of electromagnetic lenses, and 4 is detectors. This is how a construction of an electron microscope looks like. So, what do you have here? You have electrons which are excited and which are extracted from a tungsten or a lanthanum hexaboride filament. The extraction principles are similar to the way you have emission with a cathode ray tube. You have to apply some potential onto a cathode, and then you have negatively charged electrons which are coming out here. And then from this point, just from the gun emission location where you have a Venelt chamber or you have an anode here, and you have another grounding here through which you accelerate the electron through an accelerating voltage of 200 or 300 electron volts. So you're applying an energy of 200 or 300 kilo electron volts, or you're applying a potential of 200 or 300 kV, and you're accelerating electrons close to the speed of light. When this happens, you are achieving wavelengths of as small as 0.038 angstrom. However, please remember you have something called as lens aberrations, and they are more pronounced for electromagnetic lenses. And the best resolution you can achieve with a non aberration corrected microscope is around 1.3 or 1.4 angstrom. Okay, so this is the background. Now, because your source here is electron, and then you are allowing electron to interact with the sample or pass through the sample, and electrons are charged particles which can get deflected even by the ambient atmospheric conditions. So unlike you see in an optical microscope here, which is exposed to the atmosphere, you have to maintain this inside a column. And in optical microscope, the lenses are glass lenses, and in electron microscope, the lenses are electromagnetic lenses. I'm rushing through the concept here, but just to tell you the construction and the principle, I'll give you a very brief overview. And this entire thing is maintained under ultra high vacuum, where the pressures are around 10 to the power minus 6 millibar, okay, or 10 to the power minus 9 torr. Are we clear till now? Yes,
Sir.
yeah.
Sir, can we say that an electron microscope uses plasma, because plasma also has very similar principle of working?
No, the point is,
accelerated electrons.
if you look at plasma, plasma is charged ions or an ionic cloud which is created. Okay. But the plasma is still very heavy that the ions, for example, if you talk about argon ion plasma, yeah, you can still accelerate it at around 30 kilovolt or something, but the damage that the plasma can cause is quite significant. So when you have this plasma and all, you typically have them in etching devices and so on. But if you want to use it for imaging, you are better off using an electron beam, which does not have as high a momentum as some of these plasma that you're talking about, and you do not damage a sample. You still have beam damage, but it is more controlled when you use an electron beam.
Okay, sir. Thank you, sir.
Okay. So with that, what can I use TEMs for? So the point is, I've only talked about one of the applications of the electron beams in this kind of a construction. You have a similar construction which is used in what is called as an electron beam pattern generator, which can be used for lithography. You can use the same electron beam with a slightly different construction in a scanning electron microscope, which you use for surface imaging. In this talk of mine today, I'll focus largely on transmission electron microscope only. If you have questions, you can always send them across through Abhishek and they'll route them to me. Or we'll have perhaps an interactive session when some of you come over to IIT Hyderabad and we can look at how the instrument operates and where the applications are in more detail. Yeah. So I can use electron microscopes for imaging. I can measure and get information from samples. I can look at crystalline samples and see what my interplanar spacings are. And with all the information I get on the composition, on the structure, on the crystal structure, I can use to build models, both crystallographic models. And if I look at real time processes, I can get information on kinetics. I can start constructing physics based models. As I mentioned, if you're using it like a lithography system, I can manipulate matter. In particular, we've had experience in manipulating two-dimensional materials to start constructing transistors or devices in a combination of MEMS-based devices. And the types of specimens you can study are metals, alloys, ceramics, glasses, polymers, semiconductors, wood, textiles, concrete, real time devices, biological samples, cells and tissues, and so on. But the caveat here is if I prepare the samples carefully, and while I'm imaging the sample and while it is interacting with the electron beam, if I do not cause any significant beam damage and if I do not lose out on the vacuum of the column, I can image any kind of a specimen. Provided I understand what is the appropriate dose, what are the appropriate imaging conditions. So this is a broad overview of the technique called transmission electron microscope, and we'll start looking at how you get imaging inside the TEM. Now, you saw the physical construction of how the microscope looks like, but if I look at the schematic diagram of how the lenses are arranged, I have an electron gun, I have a series of condenser lenses. The condenser lenses are now focusing my electron beam either like a parallel beam or like a converged probe. And depending on how this beam is interacting with the sample, I collect the transmitted signal. That is, I have a specimen positioned here, and I have an objective lens, which is a electromagnetic field, and then I have series of projection lenses. Yes, please. Uh, we'll. Can I answer the questions at the end, Prem? I'll come back to this question at the end. Yeah. All right. So, if you look at it, the specimen is very thin and it is placed in the field of the objective lens, and the electron beam interacts with the sample, and whatever forward scattered signal I get goes through the series of projection lenses and you form an image. You can use a static beam. When I say a static beam, I use a parallel beam, and I can have something called as a bright field, a dark field, high resolution image, and you have a few other modes called as electron holography. But if I scan a beam and if I raster as a probe, I can use something called as STEM, and I get what is called as an annular dark field image or a bright field STEM image. Now, one important thing that I want to tell you here is in an electron microscope, you have either a bright field or a dark field image. What this means is if the background of my image is bright and the features that I start seeing are appearing darker, I call that as a bright field image. Whereas if I have a dark background and I start imaging and my features start appearing bright, I call it as a bright field image. Okay. So all this information that I told you now typically is a 3 or a 4 introductory lecture in microscopy. I'm very sorry, with the paucity of time, I'm trying to rush through these concepts to give you an overview of what the technique can be used for. So please bear with me. So if I look at the limitations of a transmission electron microscope, the first main limitation is as the electron beam has to go through the sample, I cannot have a very thick sample. Like somebody was mentioning here, the TEM needs a reflecting surface. The point is, for an optical microscope, you actually need a reflecting surface. But for a TEM or for an SEM, you make the sample flat for an SEM. For a TEM, you have to make the specimen thin enough that the electrons pass through. Roughly speaking, if I look at these numbers, you do not have samples thicker than 100 nanometers. And the next limitation is, as the technique is shown, is a projection kind of a technique where the information is transmitted through a sample and I collect it on a screen below. A three-dimensional object appears as a two-dimensional projection. Okay. This is called as the projection limitation. So if I see a sphere as an object and if I'm trying to image it, I only see a circle but not a sphere the way I see inside an SEM. And then there is something called as electron beam damage. The momentum that can be transferred from a fast moving electron beam can damage a sample. This is often a very significant problem for biological or soft samples or graphene or kind of carbon based materials. But for most inorganic samples, the specimens can be imaged directly in the TEM. And the specimen preparation is an art and it is a challenge. You have to really cut, grind, polish, make the specimen thin enough such that it is less than 100 nanometers, and then you can start seeing the features inside the specimen. So this is what the limitations of the TEM are. And if we go to some of the concepts which you are familiar with, how do I see something in an electron microscope? Before I go into this, can I ask a quick small question? How do you see an object? How do I see something which is in front of my eyes? Don't tell me I see it with my eyes. I want to know the physics of how you see something.
The light falls on the object and it gets in our retina.
Okay. So the light, suppose I'm illuminating an object with white light. Yeah. What is the kind of interaction that is happening between light and the object?
It will
So
absorb all
certain colors
the.
are observed and the remaining are seen by our eyes.
So you can have reflection, you can have refraction, you can have diffraction, you can have transmission. Correct? Do you all agree? I'm assuming you all agree. So when I have a simple periodic electromagnetic wave interacting with an object, it has to either reflect or it has to refract or it gets transmitted through. Correct? And when this interaction happens, I capture it with the help of a lens and it forms an image on either a screen or a detector or on your retina, and you start seeing the features. The principle with light is, let us say an object appears yellow because I see a yellow object in front of me. When white light hits this yellow object, it's the yellow color which is from the optical spectrum which is getting reflected, and then I see it in yellow color. But can somebody tell me what is the color of an electron beam? Hello?
Colorless,
Why is it colorless?
because its wavelength is lesser than the optical region.
Brilliant. So you see color only when the wavelength is between 400 to 700, as somebody wrote here. But anything which is of a wavelength of 0.038 angstrom, you'll naturally not see it. Right? So when this kind of an electron beam is passing through an object, remember you have a propagation of an electromagnetic wave. What are the two fields that are being propagated? Hello? When I say an electromagnetic signal is being transmitted, naturally, what kind of a field do I have?
The
I
electric
am
and
propagating electric field and a magnetic field, isn't it? And if you look at objects all around you, yeah, you'll always have objects which have a certain dielectric constant. Yes or no?
yes.
Yeah. Now, when an electromagnetic field interacts with a sample, which is consisting of multiple atoms which are arranged in columns in periodic fashion, which is a crystalline object, or an object has a certain capacitance or a dielectric constant. What happens when an electromagnetic field interacts with a dielectric material? Hello? What disturbs?
We can see the
Electron
formation of
propagation.
dipoles,
You can either have formation
dipole
of a
formation.
dipole, right? That is within the object. Okay. You can have polarization. Yes, you're all right. Or the main thing that I see is my sample, my probe itself, which I'm using, which is a propagating electromagnetic wave, will have a phase shift. Is it not? Yes, it can slow down. And this process of slowing down is refraction in terms of optical wavelengths. In terms of an electromagnetic wave, you can have a phase shift which is happening. Okay. So if I look at the simple general periodic notation of an electromagnetic wave in one dimension, you all agree that it can be written like this? Hello? And then If I look at a simplified version at a given instance of time, I can write it as psi x is psi naught kx. Yeah? So what is this psi naught and what is this k here? Hello? Can somebody
So
talk?
K is propagation constant.
Okay.
K is wave number.
You can call it wave number, you can call it propagation constant, you can call it kx is what? The entire kx together.
Phase.
Direction of the wave, sir.
We'll come to the directions, Pawan. Yeah, you're not
The
wrong.
phase angle.
Phase. Kx is phase and psi naught is amplitude. Okay. So if I have an optical signal interacting with a transparent medium like water, yeah, this kx here changes when light is propagating through and the velocity changes. That is how you see bending of light. Okay. If I have some kind of an absorption, or if I say psi naught is the intensity of the incident radiation, and I'm collecting the transmitted or reflected radiation, with all the physical interaction phenomena that is happening, do you guys think I'll get the entire psi naught collected on a detector after an interaction has happened?
It decreases.
It decreases. So, what decreases in terms of an electromagnetic wave when I'm collecting a signal on a camera? Hello? The amplitude, right? So, when I look at any images in general in a microscope and when I record on a camera or any recording medium, the contrast that I see, the X-ray image that you saw or a photograph that you see, these are all simply recorded variations in intensity or recorded amplitude contrast images. You're all with me? Okay. So, my next question is, if I plot this, how does this look like? Do you agree that this looks like this?
Yes, sir.
Hello? To show my sinusoidal waveform, what do I do on this? If I take a cross section, or if I take what is called as a histogram, you see there is a variation in this gray values here. Like somebody wrote here, the signal appears binary. I would not call it as binary, but you would have varying grayscale images. Yeah. And the intensity of what intensity you record is proportional to the signal you're collecting. And when an electromagnetic wave interacts with a sample, naturally, its amplitude changes and its phase changes. Yeah? This is something you all know, right? Perhaps you might have seen it in some other context, in some other scenario. But in terms of an electron microscope or in terms of microscope in general, and when you're recording information, please bear in mind that I'll always record variations in intensity or I'll record amplitude contrast images. Right? If I want to record a phase, how can I record a phase? Please remember this question. We'll come back to this. Okay. Now, can you tell me what is the difference between these two images, the one on the top and the bottom?
Decrease in intensity or
Bright
amplitude.
frame.
A decrease in intensity or it's not inverted. If I write the top one as psi naught,
Amplitude decrease.
amplitude decrease. Thank you. So if I write the top figure, it appears like this, and the bottom one appears like this. Yeah? And what is the difference between the images on the left and the images on the right?
Phase difference.
Frequency, sir.
The frequency changes or the phase changes. When phase changes in this particular equation, what is changing? If I look at this unidimensional propagation wave vector, which is represented as psi naught kx, from the figure on the left to get to figure on right, what should I change? K. Very good. So the one on the right, if I write this as psi naught x, this one would be psi naught sine 4x. Yeah. Now, here is where it gets interesting. For simplicity, I have written a wave vector where the propagating front is perpendicular or along the x-axis. Yeah. So somebody was talking about wave propagation constant or wave number or wave vector and so on. To understand this, we'll slightly look at a more complicated version of this. Are you all still with me and in phase with me now? Very good. Now let us start complicating things a little more. If you're not understanding, if you're losing me, please tell me and bring me back, okay? So what is the difference between these three images? With naked eye, can you distinguish if there is any difference in them?
No, sir.
Sir, difference in phase angle.
Sir, phase, sir.
Sir, if you look at the ending of the image, we can see that the dark fringe is moving slightly to the left.
Precisely. So if I draw the cross sections like this, if I take the red line as reference, there's a phase shift of this amount in each of these images. So if I write this as psi naught x, this is psi naught x, psi naught sine x plus pi by 3, and this is pi by 6. Yeah. So I can actually change the periodicity by changing the coefficient of x or by adding something here. All said and done, I am changing the phase term inside my electromagnetic equation. Now, how do I represent this? What is the difference between this image and the previous images? Hello? What is that inclination called as? How can I define it with? What can I define it with?
Polarization.
Very good. Polarization can cause this shift. But if I want to represent it in a vector form in the previous equation, I can write it as a sine and a cos sum. Okay, no problem. Or simply, if I introduce a wave vector which is defined as a propagating wave front, see, all you're talking is not wrong. Multiplied by rotation matrix, sum of sine and cos or a combination of x and y, you're all right. In a simpler vector notation, if I say this is my propagating wave front, with the previous image, the wave front is now rotated by 30 degrees anti-clockwise. So if I write this as k bar as my wave vector, I can represent the waveform shown on the left as psi of xy, which somebody has mentioned, is sine out of some k bar dot r bar. So if I call r as my propagation wave vector and psi naught is some phase shift, this will be my most general notation to represent any two-dimensional varying intensity. You all agree? Hello? Yeah. Now, how many of you know what is a Fourier transform? Yes, somebody raised their hand. Apurva Singh, Aditya, whatever. Ha.
We will get to know the frequency component associated with the signal.
Very good. So, for this kind of a periodic pattern, what would the frequency be? Hello? Guys, is my question not clear, or how do I switch from this to a frequency domain? Anybody? Of course, that is what. You see an impulse, yeah, okay. So what I then see if I apply a Fourier transform on this is I can see periodic variations of the intensities. So whatever I had as the amplitude or the maxima would be at one point, and depending on whatever components I decompose this periodic image into, I see some kind of a repetitive pattern, but I see some kind of spots in 2 dimensions instead of this kind of a varying intensities. We'll come back to that, but please bear in mind, and this kind of repetitive peaks or repetitive spots that I see has some significance to a crystalline sample. Okay. Suppose instead of having one wave vector which is represented with an equation like this, if I have combination of two vectors which have propagating fronts along the x-axis and the y-axis together, I see an image which appears like this. Okay. Now, when I look at what is called as a high resolution TEM micrograph, if I imagine atomic columns sitting in like this, and when an electron wave interacts with periodically spaced columns, the distribution of atoms oriented along a particular crystallographic orientation appears as an interference pattern that you see here. And that kind of an image is called as an HRTEM micrograph. Okay. So that is some kind of a signal processing route of understanding what information you get from a transmission electron microscope. Okay. So with this, I will switch to something which is slightly simpler. Prem Babu, I'm sorry if you cannot get it. I'll explain it in more detail in a more elaborate course. What I simply said is when an electromagnetic wave is interacting with a crystalline sample in which atoms are arranged in periodic fashion, yeah, I will start generating an interference pattern at the exit plane of the sample. And if I record an image of that, the spacing of the atomic columns I see appears like the interference pattern which you just saw. Okay. So a high resolution TEM image you get from a transmission electron microscope is essentially a pattern generated because of interaction of electron beam and multiple electron beams from the columns of atoms interfering with each other, producing a periodic pattern. Is that clear? Precisely, Anish, you're right. You can decode this by looking at what the interplanar spacings are and what kind of crystal structure you have. And with complementary diffraction techniques, you can understand what kind of a crystal structure you have inside a sample. Okay. Now, I was mentioning that the samples have to be very thin so that you have an interaction with the electron beam. So for this, how do you prepare specimens is what is important. So I'll quickly talk about specimen preparation. Typically, most common specimen types are metals, ceramics, polymers, thin films, nanoparticle suspensions, and so on. I'll focus only on simple methods for ceramics and thin films. The easiest case is if you have nanoparticles or powders, I can crush them, grind them, ultrasonicate them, and drop cast them on a TEM grid. So I can crush and grind them using a mortar and a pestle, and then I can drop cast with a pipette like this. So there is something called as a TEM grid. When I show you an example of specimen holder, I'll show you. So essentially, you have a small, very thin electron transparent carbon membrane on top of which you can drop cast these carbon nanoparticles, whatever you prepare, and then you can put it into an electron microscope and see the sample inside the microscope. If you have a metallic sample or if you have a thin film, you have to take a bulk sample, you have to grind it, you have to make it less than 100 microns, in which case you have something called as electropolishing. If it is a conductive sample, if you're sectioning and then you do something called as dimpling, You can use an argon ion plasma to thin down a sample, and you have something called as ion milling. I'll show you the examples of how these look like. So when I section a sample and cut it and make it thin as a small 3 millimeter disc and make it less than 100 microns, I can place it inside an electrolyte bath like this, and I can shoot 2 jets of electrolyte and make the sample my anode. The setup looks somewhat like this. And then I can prepare a small hole inside the sample, and it becomes electron transparent. Or if I have a cross-section thin film sample, I have to do the same cutting, sectioning, and grinding. And I place a sample here, and I have a rotating wheel and a rotating platform here. And this is called as dimpling. And I reduce the thickness of a sample. So essentially, if you imagine, I have a thin cylindrical specimen like this, either by ion milling or by electropolishing. I have to make a small hole inside the sample. So this region now becomes electron transparent. So if I look at an ion mill, this is how the sample looks like. I have 2 argon ion guns, and by impinging ion beam onto the center of a specimen, I can create a small hole, and I prepare a TEM specimen. So essentially, on a very thin sample, when I form a hole, next to the hole, I have an electron transparent region, and that is how a specimen is prepared. But these are bulk specimen preparation techniques which may or may not be very effective for the kind of samples you guys would be seeing. So I've rushed through this particular example. But there's a technique called as focused ion beam SEM, which is more effective for the kind of semiconductor samples that you want to look at. So for this, if I have a sample like this, I have an SEM and I also have a gallium source in the SEM. And with the gallium ion beam, I can etch and remove the top layer of a sample. I could see some features of interest like this. The sample image you're seeing here is an aluminum sample, and this is what is called as a grain boundary. And my interest is to prepare a cross-section sample here. So what I can do is, the way you do lithography in clean room processing techniques, I can put in some kind of fiducial markers, or I can make some X kind of shapes here. And these markers would be used as a guideline for my specimen to direct my ion beam to form a trench here. Essentially, what I'm doing is I shoot a beam of focused gallium beams and I raster them in this particular region here, and I mill and remove the material in this area, and I'm left with a thin sample here. So if you look at the fabrication routes, this can be categorized as a sort of a top-down approach where you are taking a bulk sample, cutting and sectioning, or digging some trenches, and you're coming up with a small sample here. And if I look at the cross section, the sample looks like this. The width of this sample can be approximately 10 microns. The length is maybe 5 microns, but the thickness is always made less than 100 nanometers, such that you have an electron transparent sample. Now, where and why or how is this technique useful is, if I make some circuits, if I make some patterns on a silicon wafer, and if I want to see how the interface is, the exact same way, I replace this with a silicon wafer, and I can section and make a small sample and understand how my interfaces are, how my bonding is, how the patterns are, how the material is getting the properties, or if there is a failure, how the failure has happened. So this particular characterization technique, by combination of scanning electron microscope, FIB, TEM, cross-section specimen preparation, and so on, I start looking inside the materials and I establish a link between the internal crystal structure, the microstructure of a material, to the properties of the material. So that is the whole aim of this characterization of materials. Are we still in sync?
Yes, sir.
Okay, good. So I was talking about how the sample once prepared is taken into the microscope. Because the microscope column is inside ultra high vacuum, this is how a grid or a TEM grid looks like. If any one of you ever has prepared a TEM sample or is going to work preparing a TEM sample, this is the simplest arrangement you can have. You have a grid which is made of a metallic conducting copper or something, and this little thing you see here is an electron transparent copper membrane, and you drop cast sample on this. This grid goes inside a small specimen rod which appears like this. And this entire assembly, you can see there are these O-rings here. There is a load lock inside the electron microscope for a side entry specimen holder. And you insert this particular specimen rod into the microscope column, and only this portion enters into the ultra high vacuum area. Now, there is a reason why the specimen holders are designed like this, because you have to maintain the entire column, which is about 3 meters high under ultra high vacuum. And unless you have a load lock and a very small area which you are venting and putting a sample in, you cannot do imaging very quickly. Because if I have a 3 meter long column, venting such a column and pumping may take days together. So typically, the designs are made in such a way, and physically, because of the limitations of the size of the electromagnetic lenses and various other engineering design constraints, typical TEM specimen is 3 millimeter disc, and the thickness has to be less than 100 nanometers. And it is inserted into the microscope with help of such a specimen holder. Okay. So if I look at what happens when a specimen is put into the microscope and I switch on the electron beam, I generate a range of signals. How are we guys doing? Are you still in sync with me and are you understanding?
Yes, sir.
So the reason why I'm asking this question is, if I go into the complete signals inside the TEM, and if I explain all of them, I might need perhaps 3 to 4 lectures. But I'll simplify this, I'll cut short. I have a very high energy incident electron beam. When it strikes a sample, a range of signals are generated. The origin of the signals is because of the scattering that is happening. That is because of the interaction of this electron beam with the specimen. And the scattering can be divided as an elastic signal or an inelastic signal. Can somebody tell me what is elastic and what is inelastic? Hello?
Elastic means initial and final energy is the same, and like inelastic means some energy is lost.
So the
What is
probe and the signal, if they tend to have the same energy, then the probe would have the signal would have undergone an elastic scattering. Correct? But if there is a loss in the energy, then you have what is called as inelastic signal. And all the examples you see here, whether it is characteristic X-rays, whether it is Auger electrons, or whether it is electron hole pairs, or Bremsstrahlung X-rays, or electron energy loss spectroscopy signal, these are all a consequence of an inelastic event. Typically, when I take an electron microscope and I have an accelerating voltage of 200 kilovolt, approximately 93 to 95% of the interaction that happens is elastic scattering event. And about 5 to 7% that you get is an inelastic signal. And this inelastic signal depends on the type of atoms that are present inside the sample. For example, if I have silicon as my sample, the characteristic X-rays of silicon have a certain energy. If it is copper, that has a certain energy. If it is gold, that has a certain energy. So if I collect this inelastically scattered characteristic X-rays, and if I form a spectrum, I have something called as energy dispersive X-ray spectroscopy, and I can get to know what elements are present inside my sample. And if I collect all the elastic scattered signal, I can get to know how my atomic planar spacing is from what is called as diffraction. I can record an image which is predominantly from the direct beam that I get here. So I can get either a bright field image or a dark field image. I can see morphological features inside the sample. I can collect the diffraction pattern and I can get the crystallographic information. Or I can collect the analytical signal from the inelastic scatter and I get to know what materials are inside my sample. So broadly speaking, I can use a transmission electron microscope to get analytical, structural, morphological information at one go inside the material. And that is why this is a very powerful tool. Okay? So if I look at the contrast mechanisms, like I mentioned in the very beginning, I mainly have what is called as an amplitude contrast, where I see two-dimensional distribution of the variations in amplitude, and I have what is called as a phase contrast. Okay. So if I look at the amplitude contrast, broadly, I can get a signal from a specimen which is from the direct beam or a beam which has scattered at a certain angle. Okay. So if I'm collecting the signal from this particular direct beam and I'm recording the information on a bright background, I get what is called as a bright field image. This concept will become a little more clearer with the next slide when I show an example. But when I record an image from a slightly deviated beam which is scattered at a certain angle, and I record an image, I get what is called as a dark field image. So what do these mean? If I look at a sample, this is again a similar aluminum sample. So if you look at this particular image here, this is a grain, and if I get a sample prepared across this cross section and I see the same thing inside a transmission electron microscope, from the beam which is deviated at a small angle, if I record the image, my background that is being recorded on a detector is all dark, but only the beams that have undergone scattering because of a deviation of some features present inside the sample like this, or a grain boundary, or a defect, or a crack, or a secondary phase will start appearing brighter like this. Whereas when I'm recording the image by illuminating the entire specimen with a parallel broad beam, the background is all bright and the features start appearing darker here. If this particular concept is not very clear, we'll have a little discussion on it towards the end of my lecture. But the same sample, when viewed in bright field mode and dark field mode, appears like this. The same feature, which is appearing darker here, starts appearing brighter in this particular mode of imaging. But what you can notice is there are a few additional features which are not very evident over here, which are appearing more predominantly in this particular mode of imaging. Okay. So when I'm trying to look at some kind of defects inside the sample, so if you look at any material, any kind of a sample that is used in an electronic circuit, there are certain defects which are formed, like dislocations or grain boundaries or defects. If I want to image the defects, this mode of imaging called as dark field mode works better because the defects are specifically visible by orienting the sample by satisfying certain crystallographic criteria. Okay. So if I look at imaging in a conventional TEM mode, I can start seeing features inside the sample. I can correlate with other techniques and I can start seeing what information I have and how the properties of material change. This is an example from a metallic sample. I'll not focus much on this because it is not relevant to the particular crowd. I'll go into what is called as a phase contrast image. Somebody asked me, do we decode the interference pattern and get the atomic structure? Yes. And somebody did not understand on how an interference pattern looks like. So imagine I'm looking at a small region of a specimen which is oriented along a certain crystallographic direction. So what do I mean by this? Do you all know what is a crystal structure inside a sample? Yeah? So, do you know cubic, hexagonal, orthorhombic? You've heard of these? Bravais lattices? So, if I'm looking at a projection of a cube from the top view, how does it look like? Hello?
A square, sir.
You see it as a square. So if I have atoms arranged like a cube, and if I look at it from the top, I start seeing them as a square. So that is precisely what you're seeing here. So from the top, if a plane propagating electron wavefront interacts with a sample which is oriented like a cube, but the direction of the cube is such that the axis of the cube is along the electron beam direction, and the top view, which is a square, is appearing like this. So each of these dots you see here are atoms of some material inside a cubic crystal that you're seeing. And this periodic arrangement of this varying bright and dark spots is a consequence of the electron beam and the specimen interaction that we discussed a couple of slides ago. So if you saw these wave patterns that we saw, the sinusoidal waves, I showed you a propagating wave front with vertical and horizontal forming an interference pattern. That is similar thing that you see here. Okay. So this interference pattern that you see is called as a high resolution TEM micrograph. Okay. And there's another mode where you can make the sample as a probe and then you raster. And what you see is, as I form an image by scanning a sample and I record the information from each pixel, I initially have a dark background because there is no signal when the sample is hitting here, and a detector is placed like this. And when I start scanning, and when, because of the interaction between the features I have inside the sample, I start seeing them as this kind of bright features, and I start forming an image. This is called as a STEM image. Now, why do I show this example is, you can tend to see different kind of examples of images from literature that you study. A simple takeaway that I want to give you, if you're interested in the physics of image formation, how the features appear, you can have another elaborate discussion. But a simple thing that you can see is, when I see an image, the first thing I should know is, am I looking at a dark background or a bright background? And then, am I looking at a bright field image or a dark field image? Are my features appearing brighter or are my features appearing darker? Once I see these features, what could they physically correspond to inside a sample? Are these inclusions? Are these precipitates? Are these grain boundaries? Are these defects? Are these cracks? Are these second phase regions? Are these, I don't know, defects? There are so many features that you can see inside a sample. And then this particular mode of imaging, where you get an image by rastering, what you can do is, while simultaneously an image is being formed, I can also collect an X-ray signal, and I can get physically at each of these locations what kind of an elemental information I have from EDS or EELS mapping. So you see some colorful images, the so-called EDS maps and so on. Those are generated by first collecting a stem or a SEM or a rastered image from a particular region. And from each of the pixel, I also collect what kind of elements are giving me characteristic X-rays from that spot. And then I form an image and I get a compositional map. Okay. I'll skip this contrast in STEM mode and I'll go to something which is more relevant for some of you guys who are learning fabrication. The example you see here is a structure of some nano bridges made on a silicon wafer. The background you see here, this is an SEM image, and this is a STEM image, the figure B you see here. So you look at this, there's a 500 micron scale bar that you see here. So this field of view is approximately 2.5 cross 2.5 millimeter, or 2000 cross 2000 micrometer. These are all these are all gold contacts, and at this particular region in the center, there are small bridges made with different orientation here. These bridges are all made by electron beam lithography, and the sample deposited at the center of these bridges is palladium and platinum. Okay, and if I make this kind of a chip, and the TEM holder that you saw, if I place it with a chip carrier and I introduce it into the electron microscope, what I can do is I can apply an electrical signal across this bridge and I can do real-time measurement. Now, why was this interesting is my colleagues from TU Delft were looking at these platinum palladium nano bridges. These are interesting because A, they can function as a memristor. So what happens is when I form these bridges and across this individual bridge, if I do a two probe measurement, if I apply a voltage, what you can see is the following. So I apply a forward bias. There is some change happening inside the sample. So this is a nanocrystalline palladium platinum thin film, and you see because of the electron wind force, that is the electric signal going in this direction, there is a wind force because of the vacancies that are created here. Some kind of vacancies are created. This phenomenon is called as electromigration, and a hole is created here, and all the material is transported in this direction. And when I reverse the bias, the material can get deposited in the other direction. By application of this forward and reverse bias, what you can do is you can create a device which can be used as a memristor. But nonetheless, our interest here was to see how these real-time modifications to the sample. For example, this could be inside a thin film when you apply a heat or when you apply an electrical bias. There could be local Joule heating, which can cause the grain growth, as you can see here. So for example, when I look at this region, there are these teeny tiny dots here which start appearing to grow bigger. If you see, when there is an electrical signal that is passed, you have this, and you see that the bridges that are formed are filled back again by reversing the bias. So you can do these kind of real-time experiments with TEM nowadays. And this is another example where I have a semiconductor indium arsenide nanowire. And even indium arsenide, there is an interesting thing. Beyond a certain critical current densities, these wires tend to fail. And we saw that these kind of tapered nanowires beyond a certain current, which is, I think, 2.5 amperes here, we start seeing a breakdown of the bridge. So if I zoom in here at this particular point, there is formation of a little, a cavity here. And then when this forms, what is interesting to note is at the bottom left corner, there is another feature which is developed. So in indium arsenide nanowires, we've observed that there is a phase separation, or there is separation of arsenic from indium, and the nanowires start breaking down. So essentially, the bottom line is there are multiple modes of imaging in the TEM, and by the kind of devices you use, you can do real-time imaging as well, and you can start characterizing all kinds of samples, and the information you get is unlimited. And with this, I'd like to stop to take a few questions. So thank you all. I'll not go into the examples. I had some examples of different images, but I don't think I can talk about all those examples at the moment. So if there are any questions, I'll quickly take a few. So Susan asked me about imaging in STEM mode. Yeah, so Susan, if you have an electron microscope, imagine the path that I'm defining by my palms now is I can have an electron beam coming from the top of the column and going down in parallel path. Now, with the electromagnetic lenses, if I squeeze this beam and make a small cone, and then with this cone, if I raster on top of a sample, that is, do you know how an AFM functions? By any chance, anybody? Yeah, in an AFM, you have a surface and you have a tip, and then you raster on the surface of a tip. Correct? So, likewise, instead of a physical silicon tip in an AFM, if I'm now having an electromagnetic radiation, which is an electron beam here, and I converge it like a probe, and then I scan onto the sample. So, imagine if I have an electron beam scanning onto my palm like this, there are variations in thickness. There can be changes in the composition. Suppose this finger is tungsten and this finger is nickel, this is aluminum, this is titanium. The intensities of these, because of a change in the mass and the thickness, would appear different. And when I raster, this starts appearing with one intensity. And if this is heavier, this appears brighter. This is lighter, this appears darker. So this is how, by rastering a probe, I can start forming an image. Is it somewhat clearer?
Yes, but my confusion is it as same as SEM or is it a different?
It is similar to SEM, but in SEM, you're collecting either the back scatter or the secondary electron, whereas in a TEM, you're collecting forward scattered electrons. That is all.
Got it. Thank you.
So, did you all get an overview of what a transmission electron microscope is? What are the different kinds of signals and where it can be used for? Yeah. I'm sorry, guys. I think within 1 hour, I really cannot do a justice to a broad technique and I cannot show all the examples. But this is just to give you a flavor that all the devices that you fabricate in a clean room or all the materials you look at, for example, certain semiconductors have certain band gap, or nowadays you have topological devices where you deposit a thin film and at the interface, the defect across the interface or how the film has grown on the substrate gives you a certain characteristics. If you want to know how these have formed and how do they look like and why the material gets the property, you need to do what is called as characterization. And one of the most important techniques that is used for this is transmission electron microscopy. Okay, so with that, if there are no more questions, I'd like to take leave. And Abhishek, you're online?
Yes, sir.
Yeah. Okay, so I think if there are any questions, please feel free to drop an email to Abhishek. I'll answer them patiently and I'll try to give you more references. I'm sure I may not have done justice in just 1 hour, but yeah, I mean, I hope we can have one of the modules. The next phase is these people will be coming to the clean room, right?
Yes, sir.
So if there is a possibility, we'll try to have a physical half-a-day session where I'll try to show one of the semiconductor devices and explain more of these modes in person. Yeah. So thank you all. Thank you.
Thank you, sir.
Thank you. Bye.